This time we have something a little bit different. We're looking at the series, the sum as n goes from 1 to infinity of x plus 2 to the n, and we're asked for the values of x for which the series converges, and then to find the sum of the series for those values of x. So we're not looking at does this converge or not. We're trying to find out under what circumstance does it converge. If we compare this to a geometric series, the sum as n goes from 1 to infinity of a times r to the n, we know that this will converge if the absolute value of r is less than 1. The comparison is r is the base that has the exponent of n. Here, x plus 2 is the base that has the exponent of n. Therefore, this converges if the absolute value of the base, x plus 2, is less than 1. This leads us to an absolute value inequality, and I'm going to solve it by dropping the absolute values, x plus 2, and planting the result between negative 1 and 1. So I have negative 1 is less than x plus 2, which is less than 1. And by subtracting 2 from both sides, we get that x is between negative 3 and negative 1. Therefore, we can say it converges for the set of x such that x is between negative 3 and negative 1. Having a hard time writing 3's for some reason right now. Now we are also asked to find the sum of the series for those values of x. Well, again, we're thinking about this as a geometric series. S is equal to a, the first term, divided by 1 minus r, the common ratio. And I realize I circled the answer too soon because it's a two-part answer. Here we're going to say that the sum is equal to a, the first term is going to be x plus 2, that's what happens when n is equal to 1, divided by 1 minus the ratio, which is the base, the quantity of x plus 2. Simplifying, we get that s is equal to x plus 2 divided by negative x minus 1. The next one's also a little bit different. We're going to express 10.135 repeating, so 10.135, 135, etc., as a ratio of integers. For this, I'd like to be able to express this as a geometric series. So 10.135 repeating is equal to 10 plus 0.135 plus 0.000135 plus 0.000000135, and so on. So I'll just put plus dot dot dot. Now this portion of it with all of the decimals form a geometric series. The first term a is 135 thousandths, and so I'm actually going to write that as a fraction, 135 over 1,000. And the ratio r is, well, let's see, 135 thousandths, and then 0.000135, 0.000000135. Folks, this has a common ratio of 1,000th. If ever I don't know the common ratio by looking at it, then what I would do is I would take, let's say, an nth term and divide it by the term preceding it. In this case, I would take 0.000135 and divide it by 0.135. I'll get the answer of 1/1000th. The entire sum is going to be s equals 10 plus, because remember, we didn't include the 10, but it's there, the sum of an infinite geometric series, 135 over 1,000 divided by 1 minus 1/1000th. That's going to become 10 plus 135 over 1,000 divided by 999 over 1,000. The thousands, of course, divide out. S is equal to 10 plus 135 over 999, but we were asked to express this as a ratio of integers, not as a mixed numeral. So we'll conclude by saying that the sum is equal to 375 divided by 37. We have an application. A patient is injected with a drug every 12 hours, and immediately before each injection, the concentration of the drug has been reduced by 90%, and the new dose increases the concentration by 1.5 milligrams per liter. We're asked for the concentration after 3 doses a formula for the concentration after the nth dose as a function of n, and then a limiting value for the concentration. We're going to treat this as a geometric series and then take its sum, turning it into a sequence. The first dose is going to have a concentration of 1.5 milligrams per liter. If the concentration has been reduced by 90%, then after the 12 hours, there's 10% remaining. So we're going to say that the common ratio is 10%, but we'll express it as a fraction, so 1/10. Let's lay out what's going to happen after 3 doses. The third dose gives us a concentration of 1.5 milligrams per liter. But there's still some of the drug in the bloodstream from the second dose. Now remember, after 12 hours, the concentration has been reduced by 90%, and so there's 1.5 times 1/10, the 10% remaining from dose 2. But there would still be a little bit remaining from dose 1, which would have been reduced by 90% twice. Therefore, from dose 1, we have 1.5 milligrams per liter times 1/10 times 1/10. Now, when I lay it out like this, I think now it becomes clear why A is 1.5 and then R, the common ratio, is 1/10, because we're reducing by 90% each day, thereby leaving 1/10 each day. So C sub 3 is the sum of these, which we get from a calculator, and we get this approximately 1.665 milligrams per liter. Excuse me, that was reflex. It's not approximate, it's exact. C is equal to 1.665 milligrams per liter for part A. For part B, we're treating C sub n as the sum of the first n terms of this geometric series. And so C sub n is equal to 1.5 times 1 minus 0.1 to the n. I'm expressing it as a decimal instead of a fraction, just for convenience, divided by 1 minus 0.1. And simplifying the fraction will give us that C sub n is equal to 5/3 times the quantity of 1 minus 0.1 to the n. I'll give that as milligrams per liter. And there we go for part B. Part C asks for the limiting value of the concentration, and what's implied is that we want the limit as n approaches infinity of C sub n, which of course is the limit as n approaches infinity of 5/3 times the quantity of 1 minus 0.1 to the n. That value is going to be 5/3 milligrams per liter. And we can see that after 3 days, we're pretty close to that already. But there you go.